So it's another physics question Friday, and this is a follow-up of one from, I guess, the Friday before break, which was what is general relativity. So we basically got through what is special relativity last time. Since it's been a couple weeks, I'll give a little recap of that before we move on. Then Dave has some sweet downloads for us, and then we'll do a little bit of Ampere as well. And then at the end, I will hand back the exams, and you guys did really well. I think the average was like 72% or something like that, so I was extremely happy with how everyone did. Okay, so what's general relativity? So we talked about this last time. It's basically Einstein unification of special relativity, which is essentially how Einstein made it consistent for essentially electrodynamics to be consistent with Newton's laws of motion, close to the speed of light. And he did it by connecting the energy momentum density to the geometry of space-time. So this was this picture right here, a bowling ball and a mattress where we have heavy objects around, they actually distort space-time. And so the shortest paths through this curved space-time are geodesics, which may be curved paths, right? This is the shortest distance between 2 points in a non-Euclidean geometry. But this is, in the future, these are some of the ramifications. But let's just recall what we did last time. So for the case of special relativity, well, the starting place was that if I have two inertial reference frames that are moving with respect to each other with some constant velocity, last time we showed that Newton's equations were consistent under that transformation, or symmetric under that transformation. So in other words, if I'm in an inertial reference frame, then Newton's laws of motion look the same to me. It doesn't matter whether I'm at rest or I'm moving with some constant velocity v. And so that Galilean transformation is the usual one. If I want to switch reference frames, I just add a boost that's the velocity. But then we went through the algebra and showed basically that Maxwell's equations are not. So we're familiar with Gauss's law, now everyone knows Ampere's law. Faraday's law we'll learn next week. This is just the no magnetic monopoles law. And so what we did is we tried to apply those Galilean transformations to say, okay, I have two frames that are moving apart from each other with some constant velocity, and are Maxwell's equations the same? In other words, do the laws of electrodynamics look the same in two inertial frames? And the answer was no. And so we asked, okay, well, how did this not come up sooner? And it was because the corrections only really showed up when the frames were moving at some fraction of the speed of light. And so, historically, it was hard to get that fast. And so instead, one needs to use these Lorentz transformations. So these are a new set of transformations that relate to inertial frames moving apart from each other. And the important thing here was that time now changes. So there's now some relative concept of time. So in the Newtonian physics, there's an absolute time. In this special relativity, now we have this relative time, where how clocks move actually depends on how fast the inertial frame that you're in is moving. And in fact, the closer you are to the speed of light, the slower your clock moves. Right? And so Einstein put all this together, although these Lorentz transformations were known before, and basically came up with the principles of special relativity, which is the first is principle of relativity. We already had that one. This is basically that physics should be invariant in these different inertial reference frames. And the new one was this principle of invariant light speed, that there's a speed limit of the universe, and that's the speed of light, 3 times 10 to the 8 meters per second. And so this relates then, basically, if I ask, okay, is momentum conserved between these frames? When you ask or enforce momentum conservation, you come up with the famous E equals mc squared. But there's an additional term. This additional term is basically the momentum related to how fast the particles are moving. And so now there's a direct relationship between energy and mass. Okay, so one can summarize this and put it all together. This is what I just said, that special relativity basically gives us a consistent theory of electrodynamics that's consistent with Newton's laws, and this all depends on there being this constant speed of light. And so this is a nice little picture that I stole off the internet somewhere. So basically 1905, special relativity kind of unifies space and time. Through the Lorentz transformation, right now time and space both change together. Right? There's no more universal time. But because of momentum conservation, there's also this energy-mass equivalence, matter and energy. And so it's really putting all of these things together with gravity that leads us to general relativity. Right? And so this is important because of the matter up here. Right? Gravity is really a theory of how matter interacts. We had a very good theory with a few caveats that I'll tell you about shortly. So this is the question about what is gravity. Okay, so the first thing we need to introduce, so Einstein thought about this and he came up with a bit of a paradox, and thinking and understanding what that paradox is what ultimately led him to general relativity. So this starts with Newton's first law of motion. So who can show Newton's first law of motion? thing back in physics if you like. Right, so an object that is basically not acted on by a force will just stay at constant velocity or at rest. And this is a nice picture of a motorcyclist who's doing just that after hitting a wall of tires. So this is basically telling us that we're in an inertial frame. If there's no accelerations, there's no unbalanced forces, then everything's just either going to move at constant speed, it can't change direction, or remain at rest. But Einstein thought of the following thought experiment. The thought experiment is that if I'm in a free-falling elevator, right, everything is falling with me at g, at the acceleration due to gravity, then if there's no lights and I'm just inside this elevator, basically what I'll see around me is objects that are falling with me at the same acceleration. Right? So if I have a ball in my hand or an apple in the case here, this is in the Bauman comment, this thing looks like it's floating, right? So if I'm sitting here in this elevator, then I can't tell that there's any acceleration on this apple because we're both accelerating together. Right? So this is kind of somehow leads to the question, so how do we know if we're in an inertial frame? So this was really the first step that led to all of this, is understanding that, if everything is accelerating with me, then I can't distinguish whether I'm in an inertial frame or not without talking to some outside observer. So this is the so-called weak equivalence principle. The strong equivalence principle, this is from 1907, is we assume that complete physical equivalence of a gravitational field and a corresponding acceleration of the reference system. So this is basically saying more or less the same thing as this, except now we say, okay, if I'm on Earth and I'm in a box that's not moving in the presence of gravity, then this apple is going to fall with some acceleration g. We know how to solve the dynamics of this thing. But if instead I'm far away from any massive body, I'm out in the middle of space somewhere, and I have this elevator that's being accelerated upwards with g, if I'm inside these boxes or inside these elevators, I can't tell the difference between these two things. Okay? So this is the strong equivalence principle, that acceleration and gravitational fields are basically equivalent to each other. That's the fundamental thing that Einstein realized that led to general relativity. That basically, if all of a sudden I accelerate upwards, well, this apple is going to look like it accelerates downwards because my floor is accelerating upwards and I'm attached to the floor. Whereas on Earth, this apple is accelerating downwards, I'm attached to the floor here as well. And so this acceleration could be driven by some rocket booster or something like that. Here it's due to matter. But so the equivalence here is that gravity and acceleration are the same thing, right? That's the principle of strong equivalence, that I can't tell the difference between these two things. And so once you have this, there's all kinds of interesting physical consequences. And the first one is that gravity can bend light. And we already talked about this. We talked about gravitational lensing. Right? That's essentially all this is. So here's the picture. So I have some rocket that's being accelerated upwards by some booster, and I have a photon emitter inside it. And so basically I emit a photon, and then I sit outside that rocket. I imagine maybe my rocket's made of glass. And if I sit outside the rocket, well, it was emitted from this one, the rocket's still accelerating, but as soon as the photon is emitted, it's just traveling in a straight line, right, locally to this rocket. So I see this thing moving in a straight line if I'm in an inertial frame outside the rocket, not accelerating. But if I'm inside, my feet are attached to this floor, well, then I'm accelerating upwards, and the photon is basically moving in this direction. And so from inside my accelerating frame, I see this apparent path of the photon. To me, it looks like the photon is bending. Right? Really, I'm accelerating. But if I connect this with the equivalence principle tells me that acceleration and gravity are the same, then this must basically imply that gravity can cause photons to bend or to be deflected. So this was really the first principle, and Einstein had this before he came up with the Einstein equations. This was a prediction of general relativity, that in the presence of the gravitational field, light can actually bend. And in 1919, Eddington went and looked at a solar eclipse from somewhere in Africa. And so basically the reason why this had to occur during a solar eclipse is that we needed to be able to track the light coming from stars that normally would be too dim to see in the day. We had this solar eclipse, and so this very faint line here is bent. So this basically bent line is saying that the light from this star is getting bent by the presence of our sun. Right? So this was a bit controversial, but later on and under reanalysis it totally held up. That this is really the first example, and now this looks like a not very interesting example because we have all of these beautiful gravitational lensing examples from the Hubble Space Telescope. And actually I should point out in sometime in April, a professor from St. Mike's is going to come and give a lecture on the 25th anniversary of the Hubble Space Telescope. It'll be at UVM on a Wednesday during our colloquium talk. We'll advertise it close to the date, but it should be a cool talk to come learn about what the Hubble's been doing for 25 years. Okay, so this is one of these physical consequences. Gravity can bend light, and confirmed, right? So prediction confirmed. The next one, which is really a long-standing problem, and this is consistent with this idea that we have a theory and then we think that's the theory of everything or the best theory, but then there starts to be some cracks in it, and that means that maybe we don't understand it as well as we think. And so basically it was first noticed in 1859 that, so we had a very good theory of Keplerian orbits of the planets, that basically there was a precession of Mercury that was outside what we could predict by there's lots of facts, right? So we have Mercury, there's all these other planets around, we put Newtonian gravity in, the perihelion is going to precess, but it precessed more than would be expected by Newtonian gravity. And so does anyone have any idea why is Mercury the place where this thing is going to be, it's going to show up first? If you look at this picture. Closest to the sun, right? So it's in the strongest gravitational field. It's accelerating very quickly, and so this is why this is the place where these things show up. And so one can redo the two-body problem or the Keplerian orbits in the presence of general relativity. And so this pink line here is basically what you get from Newtonian gravity, and this blue line is what you get from special relativity with some exaggerated parameters. So you see this precession. The precession means that the orbit is not just a stable elliptic or orbit, it's actually rotating a little bit. And so basically you can look at the amount of arc seconds of this precession per century and the cause from various things. So all of these were known basically in 1859, gravitational tugs from other planets, oblateness of the sun, the fact that it's not a perfect sphere. So you can see these things are really, really small. General relativity correction is pretty big, 42. So this was the missing piece, right? This was observed, 574. And until general relativity came along, there's this missing piece of about 43 arc seconds per century. And so this was really a beautiful confirmation of the ideas of GR that that there's these additional effects coming into play. Okay, so unifying or kind of putting this all together, we basically have special relativity unifies time and space, general relativity unifies space and mass or gravity. And so that one can look at it in terms of this nice picture. So basically, the deeper I am or the lower I am in a gravitational field, that means the stronger the amount of gravity that it has. So in the equivalence principle, that means the more acceleration, right? The closer I am to the center of the Earth. So the faster I'm accelerating from special relativity, the slower my clock is. So this is why time basically slows down near the surface of the Earth. And this is why we need general relativity for the GPS system, right? Because satellites are up here, we want them to stay in sync with us down on Earth, so we need GR. And then the special relativity then tells us that, okay, that also means that space must actually contract near when it's accelerating near a large massive body and spread out far away. So this is like space is flat, far from any object, and it's contracting close to an object. So this basically gives us this picture. So this is it. This is Einstein had all of this. It took a long time to actually come write down the correct equations to describe it. But essentially by thinking about how space might contract around an object, so here we have the sun, the Earth would like to go in a straight line, right? But instead, it's following the straightest line in the non-Euclidean geometry that it has available to it, which is this warped space-time around the massive body. So if it was completely flat, it would just go to this point, be here, but because of the presence of this mass, that the gravity that Newtonian gravity predicts, right? At first, even Newton was a little concerned. He was like, well, what is the force? What's really going on here? The fact is that the Earth is just following this straight line, which is a geodesic in this curved spacetime. And so then Einstein basically came up with this set of equations that relates the energy momentum tensor. So this is the presence of mass on the right-hand side. This is the Newton gravitational constant, speed of light, hence the relativistic part of it. And so once I have some mass, this equation tells me how the space-time is going to curve. Okay, so then I actually need to solve these equations, right? But it turns out that's really, really hard. So we know how to solve them in some specific cases. For example, some solutions turn out to be black holes. There's a class that we offer sometimes on general relativity that's about solving these Einstein equations. And there's all kinds of good stuff in here that's certainly beyond the scope of this course, but basically what I wanted to point out that all this came from this simple idea, the equivalence principle, that there's no difference between acceleration and gravity. Once you have that, and you have this bending, then that immediately leads you to these ideas of curved spacetime. Okay, so that's all I have to say about general relativity, and I'll answer any questions you have. Yep?
So does that mean like Neptune and I guess what was Pluto, do they resemble a Newtonian orbit or like close to it?
Yeah, that's right. That's a great question. So they're so far away that basically one can't even observe with what we have able to, our observational ability, we can't see their perihelion processing because they're just so far out in the gravitational field of the sun. Yeah.
So close to the light, close to the planet, the path will be curved, and is that causing by the gravitation or the mass?
Well, so they're all one and the same. So mass, basically, mass and geometry are the same in general relativity. So once you have mass, then you curve space-time around it, and so that means that the shortest path between 2 points is no longer a straight line, as it would be in an uncurved geometry. It's now this geodesic, right? Similar to a great circle on the surface of the sphere. When planes want to get between 2 places on the Earth, they travel along these great circles. So that's the shortest place, the shortest path between 2 points on a curved surface. And so now it's our 3-dimensional space that's curved plus time, and these are the shortest paths in that curved space-time. The curve will cause so the curve of spacetime is caused by the presence of the mass.
Yes, from function that it seems that the curve will be causing like both mass and gravitation.
Yeah, so the point is that gravitation is caused by the curvature, which is caused by the presence of mass. So these things are all interlinked. And the Newtonian gravity is some limit, right, of this. If that wasn't the case, then we certainly wouldn't believe general relativity. So one, produces a better theory, or says I have a new theory that captures these additional effects, the precession of the perihelion of Mercury, but in a limit where masses are light and things are not traveling relativistically fast, it better give us Newtonian physics. And in fact, of course, it does. Yep.
So is Mercury not the same planet as the rest of the planets?
So the precession is in plane. Yeah, so one can think of this, so this is just like a rotation of this very thing. Other questions?